enter. Good. We are 20. Today is the 24th of November 2025, 9:43 Pacific Standard Time. And today we start chapter 8, Rotational Kinematics, or angular motion. Angular kinematics, another way to say that. The exam is going to be next week, the third exam, right? It's going to be on the 3rd of December. And so far, it's going to be chapter 6 and 7. Okay. Let's see. I plan to correct your labs 2 and 3 before Wednesday. So let's add labs 2 and 3 here. 2 and 3. Don't forget that the exam is from 9:40 to 11:40. Okay. Labs 2 and 3 for now, right? Let's see here. Let me erase this thing. Two and 3 for now. Lab 4. Lab 4 is due the day after tomorrow. So just stick to lab 2 and 3 for the third exam. We are almost at the end of the semester. Huh? See, time is flying here. And rotational kinematics 1, and we're going to have lab 5 the day after tomorrow. And again, don't forget, the exam is going to be Wednesday of next week, December the 3rd. Here is chapter 8. Okay, no, see how those sections of the book are organized, right? Is rotational motion and angular displacement. Okay, just refer to the regular linear displacement that we saw before. There's a straightforward relationship between those two. And then we have angular velocity and angular acceleration, by the same token that we had linear velocity and linear acceleration. The equations of rotational kinematics, we had the equations of linear motion. Okay, and then what is new is the relationship between angular variables and tangential variables, okay? And then there's centripetal acceleration, which you have already seen, and tangential acceleration, and rolling motion. One more. Okay, we're gonna cover those 6 sections. Let's go back here to my... So here you go, type of rotational motion. Okay, what type of rotational motion we're going to deal with? We're going to cover it. It's going to be the rotation of a rigid body about a fixed axis. And let me underline that. Okay, here you go. Let me underline boldface like that. It's a rigid body. It's not a stretchable body that's stretched back and forth. No, it's rigid. It maintains its shape and form. And the axis of rotation is fixed. The axis is not, moving. Okay, it's not moving. We are going to see a case in which there is a movable axis. We're going to see one, but it's just one special case. But in general, it's going to be a fixed axis. The axis is not precessing. It's not doing any fancy motion. Okay, it's just a fixed axis, and the object rotates. Here you go. Here's a rigid body, right? My remote. Okay, my rigid body. It's rigid. It doesn't stretch. It doesn't compress. Is exactly what the word means, rigid. And suppose that we have an axis that goes, the longitudinal axis that goes through this rigid body, and this rigid body is going to rotate about this axis, but it can rotate about other axes too. It can rotate about this axis here as well. Okay, and this axis is fixed. It's not moving at all. So one longitudinal axis, right? Another transversal axis, and then you can have another axis here as well, another axis here, and any combinations, right, of axes. So what I want you to be reminded of what we covered before. I'm gonna copy and paste this thing here into our notes. Okay, we are going to apply the same concept that we had for linear motion to angular motion. Okay, so we started with the concept of the position, the displacement, my software is slow for some reason. Here you go. Displacement, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. We can extend all those concepts to angular variables as well. We can redefine those concepts for angular motion. Okay, and here what you have the angular counterpart of the linear case. Here you go. We're going to deal with the above parameters related to a rigid body, right? That is undergoing rotational motion about a fixed axis. Okay, by the same token that we have linear position. And now here at this point in time, I'm going to even to emphasize that what we saw before is a linear position. What we had before was a linear displacement. So there is no doubt, right? Linear average velocity, linear instantaneous velocity, linear average acceleration, linear instantaneous acceleration. And now we can start talking about their angular counterparts. The angular velocity we denoted by theta. The angular displacement we denote by delta theta. The average angular velocity we denote by omega. Omega average, the Greek letter omega, the last letter of the Greek alphabet. Copy and paste right in here. The instantaneous angular acceleration we denote by omega. The average angular acceleration we denote, I'm going to define all that stuff here in alpha. We use the alpha letter of the Greek alphabet. Ooh. The first letter of the Greek alphabet. Here you go. Okay. And how do you define those concepts? Oh, here you go. Here's an illustration of the rigid body. Here's an illustration of the rigid body. So, can be any form whatsoever, okay? And this rigid body has an infinite amount of infinitesimal masses that I'm denoting here. Okay, this infinitesimal mass here has a mass m1, and it is a distance r1 from the axis of rotation. And because it's a rigid body, every infinitesimal mass is rotating, is describing a circular path around the rigid rotational axis, okay? Every infinitesimal mass. Let's write that down, okay? Consider a genetic rigid object rotating about a fixed axis. See below. And I'm going to copy that figure and place here right in my notes. Snipping. Get my snipping tool here. Today I'm using just one single screen. In general, I am using my computer at home with 3 screens, but today I'm traveling. I'm in a hotel room right now, and I'm using my laptop that has just a single screen. So bear with me if I'm doing that slowly. Has to do is here you go. I finally got it. Here is the genetic rigid body. Okay. Genetic rigid body. Mass 1 is located at distance R1 from the rotational axis. Infinitesimal mass M2 is located at distance R2 from the rotational axis, and they are both describing a circular motion. Notice that, right? So let's write that down. Because we are dealing with a rigid body, comma, the infinitesimal masses M1 and M2 describe a circular path around the axis, the rigid axis of radius, right? Of radius R1 and R2 respectively. Okay? Respectively. That's what you have to keep in mind. And here's another way of representing my infinitesimal masses. Delta M. Let me put delta here. Delta M. That should be delta M1. That should be delta M2. I'm going to leave this way. If you look at the rigid body from the top, that's how the paths of those masses appear, right? The path of those masses, here you go. That's an arc path that I call S1, and that's another arc path S2. Now, the angular position is going to be measured with respect to the x-axis. Okay, that's for delta mass 1 is going to be theta 1. For a mass M2 delta M2 is going to be theta 2. Okay, and there is a relationship between this arc lengths with the theta angle. Okay, which comes from the very definition of angle. Okay. Let's see if I can get this thing here. I won't be able to copy. Let's see here. Okay, looks like I have been able to grab it. I'm gonna copy that and paste in our notes. Looking from the top, looking from the top, looking from the top of the rigid body towards the axis of rotation, okay, we see the following. Yeah, we see something like that. Okay. Note, see that the path length here is not a straight path length, but is an arc. Okay. It's not like a linear distance, but it's an arc, because that was the path that the object, that the infinitesimal mass took. And there is a relationship between S1, theta 1, and R1. And this relationship is the very definition of angle. The very definition of angle. Let's here you go. Consider a rotating rigid body with several infinitesimal masses, right? Everything that I talked about is documented here. Here you go. I'm gonna copy it and paste in our notes. Consider a rotating rigid body with several infinitesimal masses distributed throughout it. Distributed throughout it. The angular position of these infinitesimal masses is given by the angle theta. There is a relation between this angle, the distance of this infinitesimal mass from the axis of rotation, r, and the arc length, s. Okay? This relation is the very definition of a very important quantity that we call the angle, of a very important quantity that we call the angle. The relation is theta is the arc length divided by the distance from the axis of rotation. Okay? So I'm going to put it here, theta sub I, right? S sub I and R sub I. R sub I. Let's put it this way. So we can make it genetic enough. Note, see that this definition of angle is dimensionless. The unit for the angle is dimensionless. According to this definition, it's dimensionless. Okay, and let's put let's copy that, and let's discuss in more detail. Here you go. Note C that this very definition is dimensionless. Dimensionless because we have a length divided by a length. That's why I put the number 1 here. Okay? And it's dimensionless. Here you go. However, because the angle, an angular quantity has more than one unit, okay? Comma, we give a name to this dimensionless unit. Has more than one unit, you know? We also have the degree and the grade, right? Degree and grade. We give a name to this dimensionless unit just to distinguish it from the others. This dimensionless unit, we call it the radian. Okay? This dimensionless unit, we call it the radian. And we can write that down as RAD, rad. So now that we talked about angular position, don't forget this angular position with respect to the x-axis, right? Let's see here, the angular position of this infinitesimal with respect to the x-axis is given by the angle theta. Now let's talk about the angular displacement. Okay, the angular displacement, delta theta, is represented in terms with respect to a reference angle. And this reference angle can be any angle. Okay. If the reference angle is 0 degrees, then the angular position coincides with the angular displacement. Okay. If theta naught is equal to 0, comma, then the angular displacement coincides with the angular position, right? Has the same value if, right? Oh, it's much more better to work with 3 screens than with a single one. Believe me. Here you go, let's get that. Theta naught just like the angular position, the angular displacement has the same unit, right? They have a unit of radians. What's next? Okay, now you should know what's coming next, right? Then we gotta talk about the angular velocity, the average angular velocity, just like if you learned about the average velocity, right? You would know, you would understand very well what we are covering here. Here you go. Average angular velocity. Defined as delta theta over delta t. Okay, and then we can elaborate on the units of this average angular velocity. is going to be the unit of delta theta divided by the unit of delta t. The unit of delta theta, just like you saw before, is either, you can represent either as a unitless, right? Or you can represent it as a radian. That's what a radian is. Radian is a unitless unit. And delta t, we represent the unit of delta t, we represent by the second. Okay, so here you go. Radians per second is going to be our unit of average angular velocity, not just average angular velocity, but also instantaneous angular velocity. Instantaneous angular velocity. Okay, here finally. Here you go. That's the definition of instantaneous angular velocity. We make delta theta and delta t very small as it goes to 0. And if the angular velocity is constant, we call it uniform angular velocity, just like we had uniform linear velocity, right? If omega is constant, we call it uniform angular velocity. And delta theta can be written as, and delta theta can be written as, you go, delta theta equal to omega t, right? Uniform angular velocity, uniform angular motion. And we can go another step further. Theta minus theta naught okay, theta naught plus omega t, like that. And that's my equation of motion for angular motion, right? So let's compare that. The linear counterpart is v naught. No, sorry. X equal, it's not v, it's x. X equal to x naught plus vt, right? Linear counterpart. Its linear counterpart is, go. And now, just like we did for linear acceleration, we can define the average angular acceleration as well. You go. We need the definition of instantaneous velocity to define angular acceleration, either the instantaneous angular acceleration or the average angular acceleration. Okay, so delta omega over delta t. Instantaneous angular acceleration is this one here. So, and now we have this other situation in which we have angular accelerated angular motion. If you have a constant, right, uniformly accelerated angular motion, we end up having an equation of motion, another equation of motion here, that's going to be given by, here you go, omega naught plus alpha t, where alpha is a constant. What else can we go? And let's not forget, I'm going to write its linear counterpart here. its linear counterpart is V equal to V naught plus AT. And then we can do the same thing for that we did for the position, right? For the position, here you go. Let's get this one here. I'm going to take advantage of this one. Now, the other equation of motion can be rewritten as being using the same derivation we did before, omega t plus half alpha p squared. Let's write that down. The linear counterpart. Its linear counterpart is the position, the angular position, right? The angular position for a uniformly accelerated rigid body, right? Angular accelerated, uniformly angular accelerated rigid body is, okay, I'm gonna write it down. Position is this one. Its linear counterpart being this one right in here, x equal to x naught plus vt. Do you see how those linear quantities parallel closely their corresponding, their respective angular counterpart, okay? And here is a table comparing the linear quantities with the angular quantities. Unit in meter. Okay. Linear and angular, right? Position, displacement, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration, and their respective units. Okay, so I already covered that, right? I organized it differently. And now what I want, okay, here's the derivation, right? That I didn't do, but you can refer, the average angular acceleration can also be defined the same way that the linear average acceleration, average velocity was defined. And we can come up with let's come up with a table from scratch. Let's see here, table. Let's see, uniform motion, uniformly accelerated motion. Okay, x, v, and a. Let's see, parameters. X, position, velocity, acceleration. Let's see if we can do that. Uniform motion. Uniform motion. Uniformly accelerated, right? And I got put another, here you go. And here, what I'm gonna do. Okay, I'm gonna do the following. I gotta expand this thing here. I'm gonna do like that. like that. I'm gonna put everything centralized, make it look nice. Okay, those are going to be bold-faced. Those are going to be bold-faced. Oops. What else? Uniform motion, uniformly accelerated motion. Here, I'm going to split. Insert. Let's see. Do I have split here? Doesn't look like we have split, unfortunately. Let's see if I can somehow split here. Table. Insert. We're supposed to have split here. For some reason, it doesn't have. Let's see. I'm gonna do that in a different way. I have to. We have this feature in Microsoft Excel that you can split the cell, but I don't see it here. Unfortunate merge. You have merge, but no split. Yeah. Okay. So you gotta do it in another way. Good. It's gonna be like that. Admit. Oh, not this one. I want this one here. I want to delete this one, and then I delete this one. And now I merge those two. If I can do in one way, I do in another, right? Merge. See that? If they had the split, would be much quicker. But it doesn't have the split. Here's angular, and this here is linear. Here's angular. Linear, linear and angular. Position. How we're gonna copy this one here. So I don't have to type from scratch. Linear, angular, theta. Here you go. Copy that. Paste there. Omega. Oh. Okay. In this case here, the acceleration is 0. Oops. Acceleration is 0. Here in this case, the angular acceleration is also 0. Let me copy this one and paste right in here. I was supposed to start from here, right? And then what happens here? Here, V is constant. And here, omega is constant. Here you go. And then I can translate everything here, but in a different way, right? In a different way. Here is going to be A equal to constant. A equal to constant. Alpha equal to constant, different of 0. I mean constant by different of 0. You copy and paste here. This one should be copied and pasted here, but then I have to change the symbols. V V naught AT omega naught alpha T alpha T. And then I'm going to copy the other thing. Yeah, here you go. So I don't need to type from scratch. Right in here. This one is the angular equation. Here's the equation for the linear position. And I'm going to constant 1, 2, 3 constant. All right. I'm shortening this constant to const. But this close relationship is not restricted just to kinematics. Okay, it's extended into the dynamics as well. It extended in terms of the other parameters, force, for instance. Okay, we have linear force. We are going to also have angular force. If we have linear momentum, we're also going to have angular momentum, and we are going to cover that. Okay. Oh, and there is more, right? There is more. By the same token that we have this equation here for the Torricelli equation also applies to angular motion. Let's write that down here. The Torricelli equation also applies to angular motion. So if we have v squared equal to v naught squared plus 2a delta x, we are going to also to have omega squared is going to be equal to omega naught squared plus 2 alpha delta theta. And that could be another equation right in here, right? Okay, so there is no uniform motion counterpart for this equation. The uniform motion counterpart for this equation, there is, okay? There is, because there is a uniform motion counterpart for this equation because, let me see here, Torricelli equation. Torricelli equation, right? And what's the counterpart? Uniform motion counterpart, just for a equal to 0. V square, v final square is equal to v initial square, right? That would be the counterpart for the Torricelli equation for the case of uniform motion. 1027. Okay, now we are going to get into something new, okay? Everything else that you see up to now is just kind of a copy of what we did in linear motion. Now, there are some other equations that we have to worry about. How, and here you go. Next question is, how do we relate the linear parameters with the angular once, and vice versa, okay? And vice versa, okay? So we start with that very definition of angle that I presented to you. Here you go. That's the very definition of angle. You know, that's how we relate the angular parameter with the linear ones, and that's what the first equation is all about. Okay, the angular parameter theta is related to the linear parameters S and R in the following way. Okay? Which comes, don't forget this comes from don't forget that this comes from the very definition of angle. We define the angle because it's a very useful quantity. Okay? And now, by the same token that we can relate the angular parameter with the linear parameter, we can do the opposite as well. How do we relate one of the linear parameters? One of the linear parameters. Don't forget we have two, right? Is related to theta. In the following way. Oh. In the following way. Good. F equal to R theta. That's kind of obvious, right? But then we have to start looking into something that's not that obvious. We have to look at the other parameters. Here are the position, right? Position, angular position. And then we can also talk about the angular displacement. All right, here you go. Angular displacement, right in here. The angular, let's write it this way. The angular displacement is related in the following way. Here you go. Okay. Because R, now, because the R that's downstairs, R is constant, you know, in view of the fact that we are dealing with a rigid body, right? If the body were not rigid, R wouldn't be constant, R would be variable, okay? Because R is constant, since, you know, since we're dealing with a rigid body, R must be constant. Let's write it this way. Since we are dealing with a rigid body, here you go. Since we are dealing with a rigid body, comma, R must be constant. R must be constant. So because since R is constant, it can be taken out from this parenthesis without applying the delta. You go like that, right? And delta S we already know is F minus S naught. By the same token that delta theta is theta minus theta naught. Delta S is also S minus S naught, right? That's how you relate the angular displacement with the linear displacement. Okay. What else? Okay. Okay, the very here you go, I did that here, right? Now, if you want to relate the angular velocity with this linear velocity, which is in reality a tangential velocity of each infinitesimal element of your rigid body, what we have to do, we have to divide my delta theta and my delta s, right, by delta t, right? Now, if we want to find out the relation between angular and linear velocity, all we have to do is to divide both the left and right hand sides of the above equations, right? Of the above equation by delta t. Like that. And then this thing here becomes, if we make it delta t goes to 0, it's going to become the instantaneous angular velocity. And this one becomes the instantaneous tangential velocity. Okay? Tangential velocity. And this tangential velocity can be placed right in here. We can invert both quantities, right? By the same token that omega is V over R, consequently, V can be written down as omega times R. Like that. Omega R. And let's put a subscript T here to emphasize that we are talking about the tangential velocity. Here you go. Tangential velocity. Okay. 1036. Let's see. Let's finish this thing here. What else? Okay, so now we have those two equations for now. Linear quantities into angular quantities. No, all the way around, right? Angular quantities into the linear quantities. Angular quantity into the linear quantity. And now we have to go the next step, which is the acceleration, right? Vt is the tangential velocity. Keep in mind that V sub t is the tangential velocity of the infinitesimal element of your rigid body. Is the tangential velocity of your infinitesimal element of your rigid body. Let's write this way. Now we can finish with the angular acceleration, right? And see how the angular acceleration relates to the linear acceleration. That's the very definition of angular acceleration. Delta omega over delta t is equal to alpha. And what else? But we have to recall that there is a relationship between omega and V, right? So here we go. Omega is Vt over R. Next, we gotta put, let's use this one here. I'm gonna do it step by step here for you instead of just copying and pasting, right? I'm going to put my omega. I'm gonna do it this way. Here you go. Like that, right? And let's see how I'm gonna do it. Let me put it in another line so it can more didactical, right? Can become more didactical. You go, don't forget that omega delta t is something like that. And then we can go another step because R doesn't change. So we can take it out from the delta operator. I'm gonna put the R downstairs here. Okay, and now we have tangential. Delta V tangential. I'm gonna put the R outside. 1 over R. Looks better. Here you go. And now, what is this delta VT over delta T, right? There's a name for this guy. There's a name for this guy. Delta omega over delta T, you already know that is the angular acceleration. Now, the question now is what is delta V over delta T? It's definitely an acceleration. It's definitely an acceleration. But notice that is the delta V tangential, right? Because it's the delta V tangential, this acceleration, this delta V over delta T, is going to be an acceleration. Yes, but it's not any acceleration. It is the tangential acceleration. And by the way, it's a linear tangential acceleration. Don't forget, this is a linear quantity, right? And this is a angular quantity. I'm going to simplify this notation here. By putting the alpha t at the top without the 1. And now we can get our now we can put all my other equations together, each one on the side of the other. Let's see what I want. Yeah, I want to get this one here, right? See, alpha is linear acceleration over r. Omega is linear velocity over r. And then what about the other one, the very first one that we used? The angle theta is linear position over r. That's not difficult to remember that, right? Here you go. Over r, and over r. Angular quantity is linear quantity divided by r. Angular quantity is linear quantity. It's respective, right? Linear quantity divided by r. And again, angular quantity, the third angular quantity, is its respective linear quantity divided by r. That's not difficult to memorize, right? And there's one more thing that we have to worry about. Okay, let's copy this one here. And then there's one more that we have to worry about, because we can finish that and start our break very soon. Okay, here we go. I am just here writing the linear quantities in terms of the angular ones. You're writing. In terms of the angular ones. In addition to the tangential acceleration, we also have the centripetal acceleration, right? Okay, so since the infinitesimal masses, infinitesimal elements of the rigid body are describing are undergoing, right? Are undergoing circular motion, not necessarily uniform, circular motion, not necessarily uniform, comma. We must also have a centripetal acceleration, right? We must also have a centripetal acceleration. Here you go. And we know from uniform circular motion that the centripetal acceleration is the tangential velocity squared divided by the radius. Let me use it in another line. We can also here write the centripetal acceleration by substituting the tangential velocity with its angular component, right? And that's what I did here. I go in the next step, I raise everything here to the square to obtain a simpler equation. Okay, and how the centripetal acceleration can be here written in terms of its angular counterpart. Note that there is no alpha here. So that's the only one who escape that standard way, right? Of writing. The other ones, the linear ones is, or even the angular ones is the linear divided by the r, right? But now this linear centripetal acceleration, which is kind of a linear quantity, doesn't obey the same pattern. Doesn't obey the same pattern. Let's write it down here. Put them all together. And there is one more thing that we have to do. One more thing that we have to do before we get into our break. We notice that we have centripetal acceleration and tangential acceleration, right? We do have a tangential acceleration whenever the angular acceleration is different of 0. If the angular acceleration is equal to 0, then we have only a centripetal acceleration. Note that we have a tangential acceleration only whenever the angular acceleration is different of 0. However, if there is no angular acceleration, the tangential acceleration will be 0, and the only acceleration that is left out is the centripetal one, right? Centripetal one, like that. And the last thing we're going to do, we're going to, now we can, let's see if I have an illustration here for the next thing that we're going to do, so you can visualize it better. Rotational dynamics. No, I do not have it, unfortunately. Yeah. But, okay. Now, if a rigid body has an angular acceleration, comma, its infinitesimal elements will have two components, two acceleration components. Okay? And I'm going to write it down here. Here you go. Two acceleration components. I'm going to write that down here in terms of a vector, net acceleration vector. The net acceleration vector is going to have a centripetal components along the radial direction, right? Plus a tangential component along, not the radial direction, but along the angular direction, like that. Both components of the acceleration, where, here you go, 1, 2, 3, where both components of the acceleration are perpendicular to each other. The radial component is perpendicular to the tangential vector, to the tangential unit vector. Consequently, the net acceleration can be here written as, you go, and by net acceleration, I mean the magnitude of the acceleration vector, which I'm going to put the two bars, this one right in here, right? It's going to be what? It's going to be the square of the one plus the square of the other, right? You go. Square of the other. And then we got to put the square root here, just like we have with the Pythagorean theorem. But there is more. There is more because now I want to write my net acceleration in terms of the angular parameters. The centripetal acceleration in terms of the angular parameters can be written like that. And my tangential acceleration is going to be squared as well. And, oh, not here. It's here. Uh-oh. Huh. Why is it doing that? Yeah, strange. Let's see what's going on here. Some of the bugs of the program, right? Here you go. Gotta be careful about those things. Let me erase that. Good. Wow, okay, now I got it what I wanted. And what goes here? Alpha, right? Remember? Alpha divided by R, right? Alpha divided by R. We can go another step. Here becomes R squared, omega to the fourth power. So alpha squared, R to the second power. And then we can go the next step. The next step, we put the R squared in. We take common denominators, right? Common denominators. When we take a common denominator, this R squared become R to the fourth. And we finally have our final simplified equation in terms of the angular parameters. Okay, so let's see here. Here we go. Let me see. It looks like, oh, wait a minute. It looks like I made a mistake here, right? Here you go. Tangential acceleration. Oh, yeah. Tangential acceleration. Yeah, it's R times alpha. It's not divided by alpha. It's R times alpha. All right. Let's go back here. Yeah. R. Let's see. Centripetal is R omega square. Tangential is R times alpha. Let's see. Centripetal R omega square. That's good. Yeah. So the mistake is right in here. Now we can fix that. Is R square upstairs, not downstairs? All I had to do was to do dimensional analysis, right? And now, yeah, and now we got it. We got it right. We put the R square in evidence. We erase this guy here, and now the R is upstairs. Let's make sure that we have the right units, right? Here is radian square, radian to the fourth power, divided by second to the fourth power. Here is radians to the second power divided by seconds to the fourth power as well. But radians is a unitless unit, right? And all we end up having is 1 divided by s to the fourth power. We take the square root of that, we end up with 1 divided by second square. Unit of R is meter per second square. So in terms of units, our solution is correct in terms of units. And now, let's say we go and copy this one here. From angular parameters to linear parameters, right? We have 3 linear accelerations here. We have the tangential acceleration, the centripetal acceleration, and we have also the net acceleration, the total acceleration. 1, 2, 3 acceleration, 1 linear velocity, 1 linear position. It's 10:58 right now. Any questions that you have? Am I missing any questions? I don't see any. Okay. So let's see. Let's take our break now. I'm getting tired here. 10:58 a.m. That should be 11:13 a.m. 15 minutes break. And I see you in 15 minutes, okay? Thank you. Stop sharing. Recording. Okay, I'm back here. I just want to confirm with you folks, is the internet connection a good one? Do you have any interruptions, or you can hear me well?
You were kind of frozen for a second, and then the audio was kind of going out and coming
Oh,
in.
really? Is it happening with frequency or just once?
Yeah.
It's happening with frequency.
I think just now, but
Mm.
yeah, and Edith in the chat was saying that your voice was cutting out sometimes.
Really? Oh man. Okay. Let's see. Sometimes cut out. Okay, that's good to know. Yeah, let me see if I have, if the problem is my internet. I am at the hotel right now, and I'm using the, wait a minute. Oh, I was using my goodness. Yeah, me dá o, yeah, it looks like the Wi-Fi here of the hotel has a very low signal. And I was using my cell phone, and let's see, and I just discovered my cell phone died. So let me go back to the cell phone thing, and hopefully we're not gonna have any problems with the voice. Okay. Okay, so let's see here. That's the... Okay, so let's do